Right then, so we're finally here, 2009, the actual math paper that I took when I was, what I'm assuming like a 17-year-old at school. So this paper is quite fun. I don't remember any of it. This is just the first 10 questions that we'll do. I won't do any of the longer form questions. But anyway, this question here, let's start off with. So first, of course, we can just integrate this by expanding this out, and then just integrating it, then shoving in the numbers, putting in 0 is nice, isn't it? And then we're looking to make this as small as possible. But it's just a quadratic in A, right? It's more familiar if I write it like this, maybe. Let's try and minimize this function where we just complete the square. So we halve this number to make it a third, take away a third squared, which is a ninth, and combine these two fractions to find the minimum value this can be. And now I can't actually be bothered to do that. What I can be bothered to do, though, is look at the answers and notice that this one is the only one that ends or has a denominator of something with a 9 and a 5 in it. So this must be the answer. You can combine those fractions if you want to and realize that that is the correct answer for sure. But anyway, I can't be bothered. This question here then, so we complete the square on the x terms and the y terms separately to get x plus 3 all squared minus 9, 3 squared is there, and then y plus 4 all squared, and then minus 4 squared, which is 16 there. These two things add up to 25, add them to both sides to make 100. So this is a circle, radius 10, center minus 3 minus 4. So we can draw that, of course. Minus 3 minus 4 is down here somewhere, radius 10. Of course, minus 3 minus 4 is exactly 5 away from the origin, because it's a 3, 4, 5 triangle. And the radius here is 10, which means that combining those two pieces of knowledge, the closest point on the circle to the origin is this point here, which is exactly 5 away, because 5 plus 5 equals 10. So the answer is going to be 5 from our picture. C, we can answer without any algebra just by drawing a picture and using the multiple choice answers. We'll do this again in this paper. But of course, x to the 4 looks a bit like a quadratic centered at 0, 0. It looks a bit like this. It's a bit flatter at the bottom here, because when you raise very small numbers close to 0 to higher powers, they become really small, like 0.5 squared is 0.25. The numbers get really small. So it's a bit flatter in the middle, but it doesn't really matter for our purposes. This is a quadratic centered with a double root at C, so it could be over here somewhere with C here. Again, it's a bit wider than the quartic, because quartics raise up faster than quadratics do. But we can see from this picture that this only has 2 intersections. So some value of C that's far away from the origin is not going to have 4 real solutions. So this is clearly out, because I've just got an example that doesn't. But also, if I put C way over here somewhere and make it a large negative, I also don't have 4 solutions, right? I just have 2 of them. So this can't be right, because that's saying for all C below like a quarter. That can't be right. And nor can this, because this is saying for all C below minus a quarter. That's clearly not true either. And so we're left with this answer, which must be the correct thing. Now, I haven't proved that this is the correct thing, but it can be it's the only thing that it can possibly be. So like a 30-second sketch answered this question for me. If you put this into a computer, so here again, this is what I was saying about the quartic graph, the x to the 4, is it's very flat around very small x inputs, whereas the quadratic actually rises faster and then starts rising more slowly as the quartic catches up when you get bigger inputs. But anyway, what I'm saying here is this quadratic here, the blue one, has I think I put in a C of 0.1 here, and this has 4 solutions because it's got 1 here, and then there are 2 very close to each other down here. If you zoom in, what happens is the green graph rises really slowly, again because very small inputs are shoved down quite a long way when you raise them to power 4. But the blue graph comes down, touches it somewhere here, goes down to 0. Remember, the green graph is slightly above 0 here. So it touches it, the blue graph touches it on its way down to 0 at 0.1, and then touches it again as it rises faster outwards, and then touches it again when the green graph catches back up. Now, of course, you can do all of this with algebra if you want to. The recommended way of doing this, I think, would be to square root both sides here. Remember, when you square root, to use a plus and a minus, which means you're actually looking at 2 graphs. You're looking at this graph with the plus and this graph with the minus. And then what you do is you solve both of these quadratics. Except you don't really solve them. What you do is you look for when both of them have 2 solutions. So you want b squared minus 4ac to be greater or equal to 0 on both. Equal to, because you're allowed to have 2 repeated solutions on each of these to make 4 repeats total, possibly. So yeah, you do the discriminant check on either of these and you get this bound here. But of course we can just do it with a sketch, which was nice. This one's quite a nice question as well. There's lots of nice questions in here. The first 2 terms make -1. The second 2 terms, the third and the fourth term make -1. If you put them together, these make -1. They'll keep making lots of -1s, which leads you to a couple of conclusions. Firstly, if you want this to be bigger than 100, you're going to need the last thing to be a plus. Right? You can't cut it here, for instance, because then you just have -1 plus -1 plus -1. You need to end with a plus, and it needs to be an odd number, because it's the odd numbers that are being plussed. So n must be odd here. And okay, so how many pairs of numbers are there that each add up to -1 are there underneath n? Well, if you just take n to be 5 as a random guess, there are 2 pairs of -1s beneath 5, this pair and this pair, each adding to -1. And if you take n to be 7, there are 3 pairs. So to find the number of pairs, you take n, which is odd, take away 1, and then divide it by 2. So take 5, take away 1 is 4, divide by 2, and you get 2 pairs. Take 7, take away 1 is 6, divide by 2, and you get the 3 pairs. So the number of -1s here is n minus 1 divided by 2. And then you add n, because that's the last thing that you're adding here, and you want that to be greater or equal to 100. And this is just something I can solve very easily. Times everything by 2, expand out this -1, solve that very, very quickly, and we get the answer of 199 as our answer, which makes a lot of sense that it is that, because you have roughly 100 pairs of -1s beneath it, you kind of know intuitively, and so roughly -100 plus 199 is roughly greater or equal to 100, but it can't be any of these are nowhere near. Good, next question. So this is a really, have I said this every time? This is a really good question. 2 to the power of something plus 2 to the power of something is 2. Now the problem with this is 2 to the power of 0 is 1. So you could use 0 twice to get 2 to the power of 0 plus 2 to the power of 0 equals 2. That would work, except sine squared and cos squared are not 0 at the same time. You know that because of the identity sine squared plus cos squared equals 1, which means they both can't be 0 at the same time, because then you'd have a case where sine squared plus cos squared equals 0. So that can't be the case. So you can't have both of these things be 0, so that can't be a solution. The problem is that exponential functions are strictly increasing functions. Like, picture an exponential in your head. They start low and they just increase. Like, that's all they do, is they increase. So even if you put something slightly bigger than 0 into this exponential here, you get something bigger than 1, because increasing your input increases the output. The exponential just gets bigger. And that's a problem because sine squared and cos squared are both greater than 0 or equal to 0 because they're something squared. So here you've got something that's either 0 or bigger. Here you've got something that's either 0 or bigger. And so when you raise 2 to either of those things, you get something 2 or bigger. But you can't do something that's bigger than 2 plus something that's bigger than 2 to get 1 or bigger. Because 2 to the power, anything slightly bigger than 0 is slightly bigger than 1. So this is slightly bigger than 1 unless sine is 0. This is slightly bigger than 1 unless cos is 0. And you can't add 2 things that are slightly bigger than 1 to make 2. And as I mentioned, you can't have sine and cos both be 0 at the same time, because that just never happens. So this just has no solutions at all. And try making sure you followed all of my logic there. But we can deduce that therefore this has no solutions. It's quite a nice question. F then, so this is a very Tamura-like, how many solutions does this have, or trying to find conditions where it has 4 solutions. What you want to do is you want to replace this with a graph, and then you want to graph it. So it's a positive quartic, right? So it's up here, and it's got a y-intercept of k, but I don't know whether k is negative or positive, so I'm not going to put that down yet. Now the way that this has 4 real solutions, the way that it has 4 roots really, now that we're thinking about like a graph, is for it to come down here, have a minimum point down here somewhere, a maximum point here, another minimum point down here somewhere, and then turn back up, right? If its minimum point or if its turning point is up above the axis and it turns here, then it can't have 4 solutions because it can only turn once more, and then you'd only have 2 solutions. So you need both minimum points to be underneath the x-axis to have 4 solutions. So okay, let's look at the minimum points. We differentiate, we set those to 0, we can divide by 12, we can factorize, and we can find the minimum points are at 0, 1, and 3. Oh, sorry, the turning points, 0, 1, and 3. So there's 1 here, 1 here, 1 here. Which means, again, thinking about maybe what the graph will look like, this must be a minimum, so it goes down, turns up. The 1 must be a maximum, the 3 must be a minimum, and then it comes back up again. Of course, there could be some inflection points here, but I can't be bothered to deal with those, so we'll just deal with this. But what I really want to know is where the coordinates are. Remember, I wanted those minimums to be below the x-axis. So let's find the coordinates at 0, 1, coordinates, that's spelled correctly, right? I don't know. 0, 1, 3, it looks weird. When you put in 0, you just get k, obviously. When you put in 1, it's not too hard to work out, you get 5 plus k. Now, putting in 3 is annoying. you can either do the maths, you can do some fancy things with your powers of 3 if you want to, or you could just notice this 5 corresponds to this, and the 27 probably also corresponds, and it turns out it's k minus 27. Of course, you don't know whether it's minus or plus, which is a bit annoying, but that gave you a helpful hint. What I did was I did this, and then I got 27. I was like, oh good, it's 27, I haven't made a mistake. That's how I did it. But anyway, so okay, we have our 3 points. Now again, like I said, this one's a min, this one's a max, this one's a min, hopefully. And this one and these two need to be below the x-axis, and also this one needs to be above it. This one needs to be above the x-axis, because if it turns down here, minimums, maximums here, minimums there, and then goes up, that was only 2 roots, right? Turns, it goes down 1 root, turns, 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 1 root again. So that's 2 roots. So this needs to be above the x-axis, these two need to be below. So okay, k clearly needs to be negative to be below the x-axis. This needs to, k here, if k is bigger than, say, minus 5, sorry, if k is more negative than minus 5, this becomes less than 0. Like if k is minus 10, this becomes minus 5, and I can't have that. I need that to be above the x-axis. So k can only be, it needs to be negative, but it can only be as negative as minus 5, because otherwise this becomes below the x-axis, which I can't have. And so I immediately get to my answer there. This one, the 27 is far too big to cause a problem here. This is always going to be below the axis for this range, which I just decided based on these two things. And so this is my answer here. Good. G. There's actually a question, I can't remember which year it was, a couple of years in the future that was just this exact same question, basically. Kind of interesting. Sine x equals sine y is the graph. Now, of course, y could equal x here, right? Sine 30 equals sine 30, obviously. So this graph involves the line sine y equals x, which is this diagonal line here. So therefore, the answer is not this one. It's also not this one. Now, here's the sine graph. The thing is, though, that there are other ways you can get sine y to equal sine x. For example, sine of pi over 6, which is equal to 0.5, is the same as sine of 13 pi over 6. And the reason that I know that is because all I did was add 2 pi to the input. Because sine is periodic every 2 pi, when you add 2 pi to your input, you're just going to get the same thing. So I can also say, along with y equals x, I can also say this. I can say pi over 6 equals 13 pi over 6 minus 2 pi. Right? Then I'm going to get the same thing. So I can say this is a line that's on here as well, so this is just the same gradient, just with a lower y-intercept, so that's looking like this one here. At 2 pi, but also sine goes the other way as well, right? So I could just take away 2 pi instead and end up with this kind of idea. So there are lots of parallel lines for gradient 1. So could be this one. This one is the same, except it also has lines gradient minus 1. So how do we get those? Well, we think there are other ways, aside from going 2 pi into the future, of getting to the same result. For example, again, sine of pi over 6, which is equal to 0.5, is equal to sine 5 pi over 6. And that's because what you're allowed to do with a sine graph is to take any input, and that will be the same as pi minus that same input. Right? That will be the same as that, because it's symmetrical here. So sine of pi over 6 is equal to sine of pi minus pi over 6. And so this gives us another batch of solutions, right? Sine of y equals sine of pi minus y, or x, or whatever we can call it. I don't know whether this is quite correct, but anyway, the point is we can get negative things here as well, which will give us some answers, I guess. Have I written that right? I don't know. I think it's right. Anyway, this is maybe I explain it better in the other video, but I can't remember which one it was. This is definitely the answer, just because there are 2 forms of symmetry. There's either moving 2 pi forwards, or there's moving pi forwards and then backwards again. So you get positive and negative lines. In any case, let's just move on. Now, there are 2 ways of doing this question here. You can actually do it properly and come up with a proper formula for the trapezium rule with n subintervals, or you can do what I'm going to do, which is just be incredibly lazy and sketch the graph down. There's an exponential graph. It goes through this at 1, because 2 to the power 0 is 1, and when the input is 1, which is the last thing that we're interested in, 2 to the power 1 is 2. So this is the area that we're interested in estimating with trapezium rule. And it wants me to find a formula for when I split this into n intervals. Now, I absolutely can't be bothered to do that. So what I'm going to do instead is I'm going to say, okay, if n was just 1, if I just broke this into 1 interval, I would just use 1 trapezium, which would have height 1 here, height 2 there. So the area of this would be 1 plus 2 divided by 2, times the distance between them, which is 1, which is 3 over 2. So that's the area of the trapezium rule with n equal to 1. And what I'm going to argue is, if any of these are actually correct formulas for when you do it into n subintervals, then if I just substitute n is 1 into these things, I should get this result. Because if these are correct formulas, then they should work for n is 1, and if they don't, then they're not correct formulas. So I'm just going to shove n is 1 into each of these things, and I'm going to eliminate possible candidates if they don't equal that. So shoving in n is 1 to this, we get 1 over 2, because 2 times 1 is 2. 2 to the power 1 over n, well, n is just 1, so that's just 2 plus 1. And this equals, well, that's a third, plus 1 is 4/3, times a half is 4/6. So that doesn't equal the right thing, so this can't be the correct formula. Then I'm going to put it into this one, and again I get a very similar result here. This ends up being 2 plus 1 is 3, times a half is 3 over 2. So that does actually give me the correct answer. And now, I can't circle that immediately, because it might be that something else also gives me the correct answer. And if that is to be the case, what I'll do is I'll just make n2 and do one more verification, and hope that that will sort it out. But actually what turns out to happen is, when you put in n is 1 into the others, they don't work either. This one just ends up being horribly negative, which is terrible, and this one, if you put n is 1 in, just ends up being the wrong thing as well. So B must be the answer, because it's the only thing that works for n is 1. Again, you can show thoroughly that this is the formula that works, but I absolutely can't be bothered to do it, because you can read the work solutions if you want to actually see that get done. Okay, so this polynomial has x squared minus 1 as a factor. Now, let's just write this as f of x first. And now, if x minus 1 is a factor, x minus 1 breaks down into x plus 1, x minus 1. So if this is a factor, if this times something else is that, then these two things are also factors, because we can just break this into. Imagine if 15 is a factor, then that means 3 and 5 are. Like if 15 is a factor of number, 3 and 5 are also factors, because you can just break 15 into these two things. So these two things must be factors of this function. But if these two things are factors, think about factor theorem. If x plus 1 is a factor of f of x, then that means f of minus 1 is 0. And if x minus 1 is a factor of x, of f of x, that means f of 1 is 0. That's what factor theorem says. So for these to both be factors of this, which they must be for this to be a factor, then f of minus 1 and f of 1 is 0. So that's great. We can just shove in minus 1, we can shove in 1, and we'll get 0. Now the thing is, when you shove in minus 1, you get some minus 1 to powers. Now n, read this implicit information here, the polynomial. That means that these powers are integers and positive. That's what a polynomial is. It has integer positive powers. Which means that n is an integer, which means that this number is odd. And so this is just a minus 1, because minus 1 to the power of an odd thing is minus 1. Now I don't know what that is, which is awkward, but I'll just leave it where it is. This is clearly also just minus 1, so that just changes that sign. I don't know what this is, so I'll just leave it there for now. Now when I put in 1, I get something much more straightforward, because 1 to the power of anything is just still 1, so I just get this, and that needs to equal 0, remember, because this is a factor. That's what factor theorem said. And now I can just solve this. It factorizes, you can get answers of 10 and 15. But remember, for this to be a factor, both of these have to be factors. So I don't just want this one to work, I want this one to work as well. So what I do is I shove in 10 into this and shove in 15 to this and verify whether or not they work. So if you shove in 10 to that, you get this. This is minus 100, this is plus, because this becomes an 11 there when you put in 10, and that becomes a minus 1, which changes that sign to a plus. So it's minus 100 plus 250 minus 150, which does indeed equal 0, which is good. So n is 10 is an answer. Then you put in n is 15, and you should see whether that one works for this one as well. And it turns out it doesn't, because this becomes a plus 1, and so this is a minus, minus, minus. So you actually don't need to work out what these things are, you're just going to get a massive negative number. And so the only solution is 10. Good question. And the last question on the paper is an extraordinarily good question. Love this one. What you need to notice is x to the 3, x squared y, xy squared, y cubed. That looks like a binomial expansion. Now the coefficients don't look like any binomial expansion I know, but let's just check out this binomial expansion first, because that gives us x cubed, x squared y, xy squared, y cubed. So those are the right kind of powers here. Those are the right powers. How do we get these numbers? Well, notice this 8 here, so I need 8 more here. But this one's been times by 4, and this one's been times by 2. Well, okay, 4 is 2 squared, 8 is 2 cubed, got it. So all I need to do is change that to a 2y, and then I'll get 2y here, doubles this coefficient. 2y squared is 4y squared, makes this coefficient 4 times bigger, and then 2y cubed is 8y cubed, and I've got it here. So I can factorize this to be this, and then I can just raise both sides to the power of a third, because 3 times a third is 1, so that just makes x plus 2y here. This to the power of a third is, you multiply the things, you get 2 to the power of 10. But 2 to the power of 10 is just 1024. And now I'm looking for positive integer pairs that solve this. So okay, let's just start a table. Let's start with x is 1. If x is 1, then we need 2y to be 1023, but I can't have that for positive integers. And actually, that leads me to draw the conclusion that x can't be odd at all. If x is odd, then this thing becomes odd when you take it away, and then 2 times this can't work. So I can only try even x's. When x is 2, you get 1022 here, divided by 2 is 511. When x is 4, you get 1020, divided by 2 is 510. When x is 6, and so on. And you can keep doing this all the way until you get to when x is 1022. And then y just needs to be 1 to get to this. So how many pairs are there here? Well, there's just, count the y's, 1 to 511 is 511 pairs. And 511 is very conveniently 2 to the power 9, which is 512, take away 1. And that's our number of pairs here. That's the whole paper. I hope that I did as well as that when I was 17. I don't think I did. I honestly don't really remember what the score was. I think I did pretty well, but maybe I didn't do as well as I just did there. But anyway, I think I enjoyed it at the time. No, that's a lie, I didn't.